Hello, my name is Andrew Kucher, and today I'm going to be solving problem 8.063 or 8.63 in the book, which the book is Fundamentals of Heat and Mass Transfer by Bergman and Levine. And going to the problem itself, 8.63. Um, the problem is essentially asking for a like imagine like a hot plate. Whereas it says here, a cold plate is an active cooling device that is attached to a heat generating system in order to dissipate the heat while maintaining the system at an acceptable temperature. Imagine like you have a chip like for a computer and you're trying to water cool it. This is essentially what we're kind of calculating here right now. Um, but specifically, Uh, you have the capital H's and W's are the measurements for the chip as a whole, which has multiple channels and such through it. Lowercase letters for like H and W are for the dimensions of the actual channels and the fins within the channels themselves, of which the diagram that I have in my solution right here shows a simplified version of that entire system. So rather than adding the entire like apparatus, you essentially dissect it so that it's kind of like cut in halves. So you're mostly focusing on the part of the thing that's transferring heat back and forth. So it's essentially looking, as you can see, like a fin. That's also why everything is like divided by two, because it's been simplified a lot. But imagine, if you will, doubling it, stacking it on top of each other, and then when you complete that add more to each left and right side, it would look like you have a box that has a bunch of tubes running through it. But doing it this way also helps simplify it and show it like a fin, makes it easier to do the calculations and get that through your head. Um, there's a lot of initial variables. You have the height of the chip itself. You have the height of the fins. You have the width of the chip, which I've abbreviated as L, so I don't get confused between the height and width of the chip and any of my future things. You have the number of channels slash fins, which is 10. You have the initial inlet temperature for the fluid, which is 200 Kelvin, the surface temperature of the thing you're trying to cool down, which is 360 Kelvin. The fluid is moving at 2 meters per second. The conductivity of the material that makes up this entire sink is 400 watts per meter Kelvin. Now, there's a lot of assumptions. Steady state, nothing's changing with time. Incompressible fluid, the fluid is not changing over the course of the channel, at least aside from temperature. It's not like its properties aren't changing. Speaking of properties, obviously constant properties. Symmetry about the midplane in both the horizontal and vertical axis, hence why it's cut into those sort of that half scale diagram up above. There's 1D conduction. That's also one thing about the symmetry. You're basically assuming that any heat transfer outside of like the midplanes is kind of negligible. So it's 1D heat conduction in just one direction, and negligible heat transfer through the sidewalls. So mostly just up and down heat transfer through the part right here. So this would be the sidewall. So it would be up and down heat transfer through stuff like this. Um, Now, what we're asked to find is equations for finding Q and TMO, the outlet temperature for the fluid, and then using values actually calculate that out. Um, there's a lot of equations, ranging from equations from chapter 3 for fin efficiency to equations from chapter 8, like 8.45, which is shown right here as the temperature for the uh, inlet and outlet temperatures, how you can get those. This is the heat resistance, the resistance total and such. But in any case, I don't want to get too far ahead of myself. Um, I already showed you those. M1, the mass transfer is rho UMAC. So just the mass transfer, the mass of the fluid going through the tube at any given time. Um, the AT is that's the area of the tunnel. Oh, area total, my bad, sorry. AF is the area of the fins, this tall section right here. AB is the base down here. Um, that's the area kind of doing a cross-sectional analysis, as you can see kind of right here. So that's why it's a H by L. Um, Continuing on, the RSS equation is the heat resistance. So we're essentially doing heat resistances across the surface rather than obviously doing each individual thing individually. We're just totaling up the resistance of all of the separate tubes together and then doing those calculations out. Which is also why we need the efficiency for basically everything, which is from the efficiency for the fins individually. Um, we also need a Reynolds number, and we're doing, because it's a square, we need to make it a circle, do a um, comparative analysis. So that's why this DH is here. And the result of that is basically the DH is equal to H, get the Reynolds number, and then once you get the Reynolds number, you have find that that's equal to 24,150. Rho, the density of the water fluid is 984 kilograms per meter cubed. Um, and as I say here, since the Reynolds number for the DH in this case is 24,000, we can approximate H bar of the fluid itself through this Nusselt equation. What's the specific nomenclature for the equation? Through the Ditus-Boelter correlation. So this is the Ditus-Boelter correlation up here, and then multiplying that by K over the DH value gives us the H bar. And then we also have Q, which is also something we need to find, which is equal to NQ1, which is the number of fins times the mass flow times the CP of the water times the temperature difference from the inlet and outlet, because this is the temperature going into the fluid from the heat generating surface. Now to do the actual calculation, since we showed the equations up here, the variables get even longer because we need the water properties such as the density, CP, Prandtl number, mu, and conductivity of the water itself. To start, we just need we can easily get the mass flow rate, which is 0.0708 kilograms per second. The Nusselt's number from that then, for the D case, becomes 116.8 using the Reynolds number that we calculated above and the Prandtl number of the water. And then the H bar is just the Nusselt number times the conductivity of the water divided by the height of the surface, essentially, which is the DH, the theoretical diameter of the tube that we're assuming that the inner tube makes. And then that gives us a value for H bar of 12,650 watts per meter squared Kelvin. Very effective heat transfer. Now for the area of the fins, that's 6 times 10 to the negative 4 meters squared. And the area of the total area is adding up that number with the area of the base. You get 1.2 times 10 to the negative 3 meters squared. Now we need M for the fin efficiency calculations. To do that, we require the perimeter of the fins, the H bar, the H average, the K, CP, and cross-sectional area of the fluid, essentially. So you can see those numbers right here. We're pulling in H, the perimeter of the fluid, of the fins, rather. the conductivity, and then the multiplied by the area of the fins again, cross sectional area, which gives us M as 128.2 1 over meters. And then this allows us to get the fin efficiency, which is tan H times the M times H over 2. Remember that H is up here. H is 6 millimeters. And then that result is 0.952 or 95.2% efficiency. Now for the total efficiency, just 1 minus half of the 1 minus half of 1 minus the fin efficiency, which is 0.976 or 97.6% efficiency. Now we have everything we need to calculate RSS, and then it's just plugging in all the numbers, which ends up being 0.005 plus 0.0675, which is 0.0725 Kelvin per watt for the heat resistance. Now to get the total resistance of the entire fin set, just divide RSS by 2, which is 0.0362. And now we have the TMI, TS now, and pretty much everything else we need to calculate for TMO. So rewriting the equation, we have TS minus 0.911 times TS minus TMI. Remember that TS is 360 and TMI is 300 Kelvin. So doing that, we get TMO as 305.3 Kelvin. And using that and TMO to get the energy put into the fluid itself, remember that we have 10 fins, so we're doing this for 10 of the separate cases. We have 10 times the mass flow 0.0708 times 4184, which is the CP of the water up here, and times 305.3 minus 300. So this gives us a Q of 15,700 watts, which is heat flow from surface into the fluid. I'm just gonna, this is a lot, so I'm just gonna give a minute on the each page just to let you look at it. For this, it's as I said, a lot of equations. That's why they ask for the equations before you even start doing the calculations. There's a bunch of equations that are being pulled from like different chapters, referencing the Nussel number, the keeping track of all the areas for the actual fins and all that stuff, simplifying it down to be reasonable to actually calculate for. Uh, this is a lot. So just gonna give a few seconds on each page just to make sure you can look at it. All right. All right. Well, thank you for listening. Hope this was helpful and informative. And yeah, have a nice day.